physical practice what is meant by negative frequency. Just to measure frequencies are all real positive numbers and so on, but there we can use the symmetry property. Remember that I could also write this, for instance, I could also write this as p over pi integral minus infinity to 0 d omega prime imaginary chi of omega prime over omega prime minus omega plus an integral from 0 to infinity d omega prime imaginary chi of omega prime. I have this, and in this I change variables from minus omega prime from omega prime to minus omega prime. Then this changes sign, but this becomes infinity to 0, and that flips through and I get 0 to infinity, and I get this. There is a minus sign here, but imaginary minus omega prime is minus imaginary omega prime because it was an odd function, so that kills this sign here and you get this plus. So I could in principle write this whole thing as just inside here 1 over omega prime plus omega plus minus omega. And I add these two guys up and you end up with omega prime squared minus omega squared and then a 2 omega prime on top. So its principal value 2 over pi, this guy goes away and I get omega prime imaginary chi of omega prime. This is equal to the real part. So now we are fine. No matter what omega is, for instance a physical positive frequency, it says the real part of the susceptibility at that frequency is a sum or integral over all other real positive frequencies running from 0 to infinity, this with this kernel omega prime over omega prime squared minus omega squared. You could do the same thing for this guy here, except it will be a minus sign which would appear, and then you would get an omega rather than omega prime in the numerator. So apart from some sign changes, you would get an omega here and you get the same denominator out here. So we have succeeded in expressing for a generalized susceptibility using analyticity, which ultimately arose from causality plus the retarded response and so on. We have succeeded in expressing the real part of the susceptibility as an integral over the imaginary part and the imaginary part as an integral over the real part. Okay. So these two obey consistent, they have to obey these relations to be consistent with each other. It is also clear immediately that neither of them can vanish identically without the other one also vanishing completely. These relations are called dispersion relations. The Hilbert transform relations are called dispersion relations. In physics, they are also called Cramer's Kronig relations because they were originally derived in the context of the refractive index. So that is why the word dispersion relation got put in there. So it related the dispersion coefficient or the dispersion measure of dispersion to the absorption coefficient and vice versa in this fashion. Now all that is gone in here is causality. That is the primary thing. The reason for the analyticity was the causality, and causality ensured that you had a Fourier Laplace transform which made the susceptibility analytic in a certain half plane. Which half plane it is depended on my Fourier transform convention. Had I chosen the opposite convention, had I written a function of t as dt d omega e to the plus psi omega t, it would have been the lower half plane which was analytic for the susceptibility. That is not important. What is crucial is the fact that in one of the two half planes you have this analyticity. We will compute this susceptibility in a little while. We will compute it for some physical system like an LCR circuit for example, and then you will discover that it explicitly has poles in the lower half plane, as it should, because if it were a constant, if it were analytic there too, then the whole thing would just be a constant. Okay. Now let us go back and look at one assumption we made here and see what we can do about that. But it might turn out that this susceptibility does not vanish as the frequency goes to infinity, might go to some constant, for example. Suppose it, pardon me? It may not, yeah, for a huge variety of cases it may not vanish at all, it may just go to some constant at the end. What would you do? Then this assumption that I made is incorrect. I assumed that this big semicircle contribution was 0, that is no longer true. Well, suppose it turns out that chi of omega prime goes to some constant, say not equal to 0, as goes to infinity in the upper half plane. I can do the same calculation as before, but recall what happened. We had a contribution from this gamma d omega prime chi of omega prime divided by omega prime minus omega. My argument was that when this omega prime was of the form r e to the I theta, very large R, then this R and that R cancelled each other, and because this went to 0, the contribution from the integral went to 0. But now it is going to some constant. Well, you can still evaluate it because that constant is chi infinity, and this R will cancel against this R, and you have an integral from 0 up to pi. So you have an extra contribution which will be of the form I pi chi infinity, some constant which you know already. So it does not affect the dispersion relations, you can take this into account, you can do this, no difficulty here at all. It is another matter if it does not go to a constant but goes to a function of omega, then you have to worry about it, you have to do something else. But even here you have a problem, because I assumed that if omega prime goes to 0 along any of these directions, in any direction whatsoever, this chi went to the same constant chi infinity. There is no reason why that should be the case. Along different rays it might go to different values, might go to different constants, say it smoothly changes or something like that. Then I can't do this, I can't do this integral at all. What I then do is a clever trick called subtraction. What you do is you say, well, I have to pay the price somewhere, I have to know this susceptibility at some point. Let us suppose that I know the value of the susceptibility at some point omega naught. I have to know that as input. I do the same thing as before, this is omega, this is the omega prime plane, but now I define my function f of omega prime not as chi of omega prime over omega prime minus omega, but rather as chi of omega prime minus chi of omega naught divided by omega prime minus omega naught. I define it in this fashion. Now look at what happens to this function here. This is analytic in the upper half plane, it does not go to 0 at infinity, but if it goes to 0, if it goes to a constant or does not rise more rapidly than omega prime itself, then this function here still behaves like, for very large values of omega prime, it still goes to 0 on that semicircle, because now you got a d omega prime with a capital R, that capital R will cancel against this, and as long as this does not go as fast as omega prime but say like square root of omega prime or some power, this factor will take care of it out here. So this will work even if chi of omega prime did not go to 0 in the upper half plane at infinity, but either went to a constant or even grew or exploded, but not as fast as omega prime itself. This would work. The price you pay is that you have to give me this input information. At some frequency you need to know this. This is called a subtraction point, and this is called a subtraction, a subtracted dispersion relation, once subtracted dispersion relation.
implemented R square, then you do 2 subtractions.
That's right. So if it goes like omega squared, omega prime squared, then I need at least 2 subtractions, I need more and so on. So I add more points to this and then keep on adding those guys in the denominator out here. So it's possible, as long as it doesn't blow up like an exponential or something like that, which is completely unphysical, it's possible to write subtracted dispersion relations. With more inputs, you need this at other points. So this has proved to be extremely useful. This consequence of analyticity has proved to be extremely useful in practice. For example, in quantum scattering theory, it turns out that if you have scattering of a static potential, the scattering amplitude measures, in some sense, the differential cross section measures how much of the incident flux is scattered at some particular angle. You put a detector, and that measure is calculated from something called the scattering amplitude. That scattering amplitude is a function in potential scattering of the incident energy, if it is elastic scattering, as well as the scattering angle. Now, as a function of the momentum transfer between the initial state and the final state, as a function of this momentum transfer, it turns out that this scattering amplitude satisfies dispersion relations, is analytic. And therefore, you can write down such relationships and they serve as consistency conditions. And if you know something about this side, on this side, you can compute the other portion, etc. In that application, this thing is called the absorptive part and this is the reactive part or whatever. But there are lots of such applications in physics. In quantum field theory too, there are cases where scattering amplitudes, they would then be relativistic scattering amplitudes, would satisfy dispersion relations of this kind. They are very useful both empirically as well as to test the consistency of your calculations. So I brought this up because we will now look at some examples next time of physical response functions. Brought this up to show that this idea of analyticity actually has very deep physical implications. It is a very direct physical application in the case of linear response here in the form of dispersion relations. There are more such applications, but this is a very primary principal application of the idea of something being analytic. And notice how we went through this. We assumed that this function existed for real omega, and then I simply said there is an analytic continuation. I looked at this integral. So that shows that definite integrals can be used to define analytic continuations, and we will develop that theme a little further. Earlier I gave a method of analytic continuation by looking at series, by writing down power series, but here I did not do that. I just had a definite integral and then I argued that this definite integral itself gives you a representation of an analytic function. I will use the gamma function as an example to show how that idea can be developed to write down analytic continuation. The susceptibility in general in linear response is defined as the Fourier Laplace transform of some response function, and it is an analytic function in the upper half plane in the frequency in our notation, in our convention, and it satisfies dispersion relations whereby the real and imaginary parts form a Hilbert transform pair. Okay. Now just to give you a feel for a very specific example, let us take an extremely simple case, a very standard example, the damped simple harmonic oscillator, or in the electrical analogy the LCR circuit. Okay. And a typical LCR circuit with a voltage attached to it is going to look like the differential equation is this. So LCR series circuit, this plus R times I plus the capacitance part, and that is the charge. So it is 1 over C, an integral from minus infinity to t dt prime I of t prime. That is the total charge accumulated in the capacitor until time t. This is equal to your applied voltage V of t in the standard notation. So you have an inductance, a resistance and a capacitance, and they are in series. So that is equal to the applied voltage on the right hand side. Now we could ask what is the susceptibility of the system. In other words, given a voltage, what is the response like, the current response like, and I do the usual Fourier transforms, and it is clear that since I write I of t as d omega e to the minus I omega t, etc., when I differentiate with respect to t, I am pulling down a factor of minus I omega. On the other hand, when I integrate, I am pulling down, I am dividing by a factor of minus I omega. So it is clear we can immediately write down this is going to be minus I omega L plus R plus 1 over minus I omega C on I tilde of omega. This is V tilde of omega. It follows immediately that this is so. Okay. Therefore, I write I tilde of omega equal to, the standard notation is to write it in terms of an admittance here, a certain y. So, y of omega times V tilde of omega, where this quantity is the reciprocal of this guy. So, let us do the following, let us write this as minus and write it in this form and multiply through by I omega. So, this y tilde of omega is going to be an I omega divided by this I omega multiplies and gives me omega squared. I take out an L plus R over L I omega minus 1 over L C, which is the standard admittance for an LCR circuit. Okay. So, rewriting this, we therefore have y of omega equal to I omega divided by L times, that is the inertia term, omega squared plus I gamma omega minus omega naught squared. So, if you recall, the undamped LC circuit has a natural frequency omega naught equal to 1 over square root of LC, and the time constant of this thing is gamma inverse, where gamma is R over L. So, the LR circuit has a time constant which is L over R, and the LC circuit has a natural frequency 1 over square root of LC. So, in terms of those two quantities, this is the susceptibility, if you like. Now, this obviously has poles in the denominator, and the question is, where are these poles? It cannot be in the upper half plane, they can't be in the upper half plane. So, these poles are going to be at poles, simple poles at omega equal to minus I gamma over 2 plus or minus square root of, well, there is minus gamma squared and then a 4 here plus omega naught squared. So, let us look at the underdamped case, and this is going to become then omega naught squared. I took out the 4 in order to divide the 2 out. So, this is going to be minus gamma squared over 4 underdamped. As you know, underdamping is when omega naught is less than gamma over 2, and overdamping is when omega, this is the underdamped case when omega naught is bigger than gamma over 2, and the overdamped case will be when the sign is flipped, and the critically damped case is when omega naught is exactly gamma over 2. Okay. Now, where are these poles located? Well, if it is underdamped, omega naught, this implies omega naught squared is greater than gamma squared over 4. So, these poles are going to be at, in the omega plane, it is minus I gamma over 2. So, immediately you see that it is going to have negative imaginary part and then plus or minus certain things. So, it's going to, one pole is going to sit here, another pole is going to sit there in the omega plane. As long as there is resistance, there is dissipation. In other words, this gamma is a positive number. If you did not have that, if you had negative feedback, then of course you can have a runaway solution. If you have a wrong sign of the friction constant, then of course you have a solution which blows up. On the other hand, for physical circuits, for physical resistances, as we have used a convention, the same convention as before, the poles are in the lower half plane. Okay. So, this tells you that certainly you can expect a generalized susceptibility to have one or more singularities in the lower half plane, always. Whenever there is some dissipation in the system, this is always going to be the case. By the way, what is going to happen to it when it gets critically damped, over damped, etc. What is going to happen to these poles? Where are they going to go? The fact that they are in the lower half plane cannot change, right? That cannot change at all. So what will happen when omega naught becomes exactly equal to gamma over 2 is that this disappears and the two poles coincide. So these two guys move like this, they coincide, and after that what happens next? If I go to the overdamped case, what is going to happen? But there comes a time when this positive sign and this negative sign will cancel out and give you 0. So what will happen is this fellow will crawl up in this fashion and this guy will crawl down in this fashion and go off to minus infinity. Okay. So as you change the friction, for instance, keeping a fixed omega naught, this is how the two poles are going to wander around, but the fact is they will always remain in the lower half plane invariably. That is required by causality. There has to be analyticity in the upper half plane, and so no matter what you do, this is all that is going to happen in the circuit. This is exactly the damped simple harmonic oscillator, for which you recall that L is replaced, for instance, by the mass, this by the friction, the viscosity of the medium in which the particle moves, and that thing gives you the natural frequency, the restoring force of the undamped oscillator. There are lots and lots of other analogies. Many second order systems would have exactly the same sort of dynamics here. So this portion plus that portion, these two terms together, these guys give you the reactive part of the response, and this gives the dissipative part in this case. So it is not hard to see now that this y of omega will satisfy those relations that I mentioned, namely the imaginary part is going to have anti-symmetric behavior and the real part is going to have a symmetric behavior. You can check that out. In fact, as an exercise you should do the following. You should show that the real and imaginary parts of this y for real frequencies satisfy those dispersion relations I mentioned. In this case you can do that fairly easily because you actually have an explicit answer for the susceptibility itself, so it should be straightforward to do that. Now what can we say in general? Well, in physics what happens, in physical applications, what happens is something fairly intricate depending on the system. The simplest model you can think of for this response function, by the way the susceptibility was given, if you recall, by dt e to the I omega t phi of t, and the simplest thing you can think of for this phi of t, this response function, is that it dies down exponentially with some characteristic relaxation time. Lots of media do that, and that is called a relaxation time, the characteristic time with which this decays exponentially. So for instance phi of t could be equal to some constant e to the minus t over tau, where this tau is called the relaxation time. What happens then? So a lot of physical systems in the first approximation would behave in this fashion with one characteristic relaxation time. What happens then? This problem can be solved completely because you can now write down put this phi of t in here and compute what this thing does, and then chi of omega is equal to, well, if I put e to the minus t over tau and I do this integral, e to the minus a t is just 1 over a for positive a, or if its real part of a is positive, which it is in this case because tau is positive, and you get phi naught divided by 1 over tau, so there is a tau over 1 minus I is an I omega tau. So that is it. It is an extremely simple form for the susceptibility, and let us separate it into real and imaginary parts. I write this as 1 plus on top, and then it becomes phi naught tau times 1 over 1 plus omega squared tau squared plus I omega over 1 plus omega squared tau squared. So as promised, the real part is symmetric in omega, the imaginary part is odd, an odd function of omega, exactly as we had seen on general grounds. So this sort of thing is called Debye relaxation. This is a characteristic single relaxation time. The detailed mechanism of where this tau comes from, what is the dissipation inside the medium and so on depends on the problem, but Debye first wrote this form down, the simplest approximation. For instance, dielectric relaxation. For dielectrics, this is exactly how things would behave. Anelastic relaxation in the mechanical behavior of metals, for instance, would behave exactly the same way, etc., etc. So a huge number of phenomena are modeled by this kind of thing, this susceptibility. What do they do next? Well, empirically you know that the standard thing to do is to plot the real part of the susceptibility versus the imaginary part by eliminating the frequency, and that's got a lot of names. The most common name for it is called the Cole-Cole plot. This plots, if you like, the real part of chi versus the imaginary part of chi. In other words, you treat chi of omega as a complex variable and write down where it is for different values of omega, the so called Argand diagram. And what is it going to look like here? This is the real part and that is the imaginary part. Well, start with 0 frequency, then the imaginary part is dead 0, the real part is 1 in units of phi naught tau. So let us divide through by this, divided by this constant phi naught tau is just given by this. Okay. So the real part is at unity, it is at 1 here, and the imaginary part is 0, and that is at omega equal to 0. And what happens as omega tends to infinity? This goes like a 1 over omega, it dies down. This goes like a 1 over omega squared, so it dies down extremely sharply. And in fact, as you well know, these two form part of a semicircle. It looks like this. This point is omega equal to 0, this point is omega tends to infinity, and it is a semicircle centered about the point a half. I leave you to verify, it is a very trivial verification to show that real chi, let us call real chi equal to u, imaginary chi equal to v. I leave you to show that u minus a half whole squared plus v squared equal to 1/4, half squared. Okay. So what is done experimentally is to measure the dissipation, measure the reactive part, the dispersion, and then plot one against the other as a function of frequency and fit a curve of this kind to it. If it exactly fits a semicircle, namely if this is a 90-degree thing and that is a 90-degree thing, remember experimentally you can only do a few frequencies, so you extrapolate or interpolate between the experimental points, and if you can fit a semicircle to it, then the deduction is that your relaxation process took place with one single relaxation time. Okay. This is the famous Debye relaxation formula. On the other hand, experimentally what is found is very often departures from the experiment, from this relaxation, from this behavior. Most often what happens is that the curve looks like this. So it is an arc of a circle and it does not intersect at 90 degrees and it is not a semicircle in this case. Okay. And then there are other complicated shapes that you can have, deformations of this, etc., etc. What primary conclusion would you come to as soon as you see that the shape is not a semicircle?
Need more parameters.
You need more parameters, more specifically you need more relaxation times, that the system does not have a single characteristic relaxation time but has a whole spectrum of relaxation times. And then all sorts of complicated things can happen. For example, suppose it turned out that phi of t, so if it turned out that phi of t was equal to some lower and upper cut, between some lower and upper cutoff, so let us call this tau min, tau max, and then a whole spectrum d tau e to the minus t over tau with some spectral function sigma of tau, some weight factor out here, and then a whole lot of superposition of relaxation times, continuous superposition in this case. Then you got a lot of parameters to play with, you got this, you got that function and so on. And now if you put it in, then each of these times is going to give me a behavior like 1 over whatever it is. So for instance, real chi is going to look like integral tau min, tau max, d tau, sigma of tau over 1 plus omega squared tau squared. It is a pretty complicated function of frequency, because you have to do this integral first, and what you get is your function of frequency. It is still symmetric in omega, and the imaginary part will have an omega on top and you integrate the same thing, but now all kinds of behavior is possible, very complex behavior is possible. If you have just a set of discrete relaxation times, just a few of them countable, and a finite number, then the formula is just a sum of Debye like terms, usual single relaxation times, and it is relatively easy to analyze, but this kind of thing is more characteristic of what actually happens in the system. So this is a game which you can play depending on the substance, depending on the experiment, depending on the physical problem that you are looking at. Fairly complicated relaxation phenomena can occur. Now this is a microscopic approach to it, in the sense that it is not entirely phenomenological. What people would do here is to try to modify empirically, they try to modify the Debye form. For instance, they write a thing like not 1 over 1 minus I omega tau, but 1 minus I omega tau to some power alpha, and then the whole thing to some power beta, and so on. All sorts of parameterizations are used completely empirically, but this is a more physical approach to it, because it says you must tell me something about the microscopic mechanics, and then I compute what this spectrum of relaxation times is, so on. A little later, if the opportunity presents itself, we will go back and I will show that depending on what you measure and what the energy of the system is, how its energy is pumped into the system, this phi of t, you can write an explicit formula for it in terms of the physical observables pertaining to a system, and characteristically it is some ensemble average. If you keep your system in thermal equilibrium, deviate from it a little bit by applying the external force, then it is typically a correlation time, a finite temperature correlation time, classically or quantum mechanically, and you can actually compute what it is under suitable approximations. I will do that a little later. If time permits, we will solve a problem with a spectrum in this fashion. Okay.